Some of you may have already heard that there is a new El Nino index being used these days or mentioned. It's called the relative Nino index. So this is an article from ECMWF Tim Stockdale, who's been there for a long time, few decades. He wrote this blog, as they call it, on their site, measuring the strength of El Nino, introducing relative Nino indices. Obviously, when you have a warming pattern going on and El Nino is acting on top, we discussed whether that warming pattern is beginning to affect El Nino itself, and the answer is not so simple, even though one paper argues vehemently that SST variability has been increased since the 60s because of some strong El Ninos and La Niñas. So there is a assumption involved that increased SST variability in the tropical Pacific must be coming from changes in El Ninos and La Niñas. Makes sense intuitively. El Nino, the cycle of warming in the central and eastern Pacific, are global weather drivers, and obviously in 2026, I'm recording this in the beginning of July 2nd today. There is an El Nino brewing, and the terminology super El Nino is being used a lot, and the interest is very high. Media is really taken on itself to make this big news, and pretty much everything gets attributed to El Nino, even though background global warming is still going on. So it's funny to watch the climate community harp on global warming as if it's the end of the world, and then suddenly switch to El Nino as the end of the world and forget about global warming for now. That's not very scientific, I would say. So tracking El Nino traditionally relies on monitoring SST anomalies in the Nino 3.4 region. So anomalies comparing to some sort of long-term average, what we would call climatology, which we have discussed, and you know what it is. However, as the climate warms, interpreting these anomalies becomes more challenging. We already discussed a bit of that. Rising background temperatures can make recent El Nino events appear stronger and La Nina events appear weaker. Okay, so climatology and global warming, how do we account for them? So to address this, with the support of WMO, ECMWF is introducing an additional measure of El Nino strength alongside the more traditional Nino 3.4 SST anomalies in its seasonal forecast from June 1st, 2026. The relative Nino indices, so exactly 1 month. These indices compare the Nino 3.4 region with the rest of the tropics at the same time, offering a perspective that is less sensitive to long-term warming. Okay, there have been ideas about this before as well. Instead of computing anomalies with respect to that particular location, can we compute anomalies with respect to the global mean? So these are just kind of shifting the background with respect to which we are computing the anomalies. This will provide an additional tool for describing the likely strength of an upcoming El Nino event. Even with this adjustment, current forecasts suggest that El Nino may be unusually strong later in this year, 2026. What is the motivation for change? The traditional method of measuring El Nino uses an index based on the average value of SST across a large region of the equatorial Pacific, the so-called Nino 3.4 region, which goes from 5 north to 5 south, so deep tropics, and 120 west to 170 west. So that is in the central eastern Pacific to around the coast of South America, Galapagos, towards the date line. Here is the picture of the anomalies for 2026. Anomalies and extremes in sea-surface temperatures for May 2026. Color categories refer to the percentiles of the temperature distributions for 1991-2020 reference period. When you compute percentiles, you have to use a background climatology as well, or a reference period. The extreme coolest and warmest categories are based on May rankings for the period of 1979 to 2026. Values are calculated only for the ice-free regions. Areas covered with the sea ice and ice shelves in May 2026 are shown in light gray over here in the Arctic and Antarctic. The map outlines the Nino 3.4 region here, which is used to monitor the El Nino conditions. So you can see that this is a tiny little piece with so much warming going on all around. So can we still continue to use the same Nino 3.4 index? The average SST for a given month is compared to a climatological mean value, typically based on a 30-year period, to give an anomaly relative to that climatology. This approach has been used for many decades. Just how long the climatology has to be with respect to which we compute anomalies is being debated in many ways, but 30 years is just randomly accepted as a valid number of years. This approach has been used for a long time and is suitable when climate is either stationary or changing very slowly. However, global and tropical temperatures are now warming fast enough that this approach has some drawbacks. The size of the Nino 3.4 SST anomalies depends on which period is used to define the climatology, since the 30-year mean values defining the climate has been increasing by about 0.1 degrees C per decade. And you are dealing with Nino 3.4 themselves, which are often of the order of 0.1 or 1. Also, the general level of warming in the tropics makes it easier to reach high absolute SSTs during El Nino events and harder to reach cold temperatures during La Nina events, so periods of significantly negative Nino 3.4 SST anomalies. There is in general an asymmetry that we discussed before, that La Ninas don't get as strong as El Ninos in terms of anomalies. Thus, whichever fixed climate period is used, anomalies show a tendency for strong El Ninos and weaker La Ninas in recent years. But is it fair to say that El Nino events are becoming stronger and La Nina events weaker? That's what often happens, right? You say, let's look at the impact of global warming on El Niños, and you say El Niños are getting stronger and La Niñas are getting weaker. El Niño variability arises from a couple of variations in oceanic and atmospheric dynamics involving equatorial winds, oceanic upwelling and heat budgets, and changes in the location of deep tropical convection moving from west to east. Typically, these processes depend more on spatial temperature differences across the tropics than on absolute temperatures, SST gradient anomalies, pressure gradient anomalies, etc. This motivated the concept of relative Nino indices, which are defined as spatial anomalies measuring how warm an index region is compared to the tropics as a whole at the same point in time, rather than the temporal anomalies, which measure how warm the index region is compared to the same location at different times. You understand? Spatial relative warming versus warming in time. Anomalies typically are warming with respect to the climatology, so that's time, not space, even though you are defining it at a particular location. Defining relative Nino index, then we define relative Nino index R Nino anomaly as follows. R Nino anomaly is S Nino minus tropical anomaly. So where Nino is the SST index in the region that we are typically using, and trop is the average SST across the tropical region. So now you are looking at 20 north, 20 south, and S is a scaling factor. So S is multiplying Nino region anomaly minus tropical anomaly. So that makes sense given this tropical warming with a certain pattern, for example. Okay, so to express our relative Nino index as an anomaly, we remove the mean climate of the Nino minus trop difference over a reference period, in our case 1991 to 2020. Again, with some scientific understanding of the warming rates in the recent years. If the Nino region and the tropics have the same temperature trend, then the choice of the reference period has little effect, so Nino minus trop will be close to zero. In this sense, relative index is much less sensitive to global warming than the traditional index. However, if Nino region has a different temperature trend to the rest of the tropics, the choice of reference period makes a difference, meaning the relative index is not totally immune from climate change. So this accounts for spatial warming impact. Long-term changes in the relative index would reflect long-term changes in the spatial pattern of tropical SSTs, which would inevitably be associated with changes in atmospheric circulation. This is a dependence of the relative index on climate that we are happy to include in the definition. So why is a scaling factor needed? Then the scaling factor S is introduced so that the relative Nino index has the same amplitude of variability as the corresponding traditional Nino index. This is to make the new indices easy to use in any existing decision processes, effectively replacing the traditional index. So if you create a new index that suddenly looks much bigger or much smaller, then people may get confused. So you scale it so that you are remaining in the same relative magnitude. A different scaling factor must be used for each calendar month. That's important to understand. The decision to use such a scaling factor has been agreed during WMO discussions in consultation with the operational services, so that climate forecast centers are using altogether the same process, and forecast centers are involved as well from around the world. We calculate the scaling factor S as S equal to sigma Nino anomaly divided by sigma Nino anomaly minus tropical anomaly, where sigma is the standard deviation of the index for a given calendar month. So S is done for each month of the year. We estimate this over a 50-year period for 1971 to 2020, and we choose to linearly detrend both time series to reduce any contamination from the temperature trends, although this makes very little difference at times of the year when Nino anomalies are large, that is, let's say fall and winter months. Some observed data sets have higher levels of smoothing than others, which means that the variance of Nino anomalies is slightly lower. To remain consistent, the scaling factors should be appropriate for the dataset being used. So monthly and then data dependent as. At ECMWF, scaling factors are derived using high resolution SST datasets that capture El Nino peak amplitudes well and are considered suitable for both our observational and model derived Nino indices. The scaling factor represents a physical reality. What is it? When SST in, for example, the Nino 3.4 region warms up, the tropical mean SST also warms because the Nino 3.4 region is included in the tropical mean. Thus, the difference between the Nino region and the tropical mean, Nino anomaly minus tropical anomaly, is always smaller than Nino anomaly alone. So a scaling factor S greater than 1 is required. This is kind of technical discussion, but we should just go through it. But we'll look at the scaling factor here. For example, the scaling factor used at ECMWF for the Nino 3.4 region, calculated as a function of calendar month going from January to December, you can see that it has a peak in spring months and then a minimum in summer months and then rises back up during fall winter months. So when Nino is peaking in the fall winter months, S is high. This spring warming is the annual flattening of the SST gradient, and the entire tropical Pacific is also experiencing this together with the spring warming. In fact, El Nino warming extends beyond the Nino 3.4 region. As an El Nino event matures and eventually starts to decay, El Nino induced warming spreads across the tropics. Obviously, the warm water discharge and spilling of the warm water towards the east is spreading as well. It's not, the anomaly is trapped to the equator in the way we look at it, but El Nino-induced warming spreads across the tropics. This results in a scaling factor which varies with season, as we see here. Values are relatively low in July and August when El Nino event is typically in the early stage of development, and are high in March, April when tropic-wide warming is still present, but the anomaly in the in the core Nino 3.4 region is weakening. So you are, there is a evolution period, and then there is a decay period of El Nino, so you have to be careful on how you do it. Because the scaling factor is a ratio of 2 standard deviations, it's reasonable to question how accurately it can be estimated from only a 50-year sample. However, the physical nature of the relationship means that the ratio is relatively stable. So we are justifying things based on what we know about the system. Additionally, the chosen period has a high amplitude of El Nino variability, which also helps us obtain an accurate estimate of the scaling factor in terms of range of El Ninos within the scaling period, or a period used for scaling factor. So how does the relative Nino index compare then? That's the key of all arguments, right? Comparisons between the traditional and Nino 3.4 SST anomaly show that the two are highly correlated. They should be. Which we see here in a minute. However, there is a clear difference in the trend. For early years, the relative index is higher, and for later years, it's lower. Apart from this trend difference, there is very good agreement on the amplitude of El Nino peaks and La Nina troughs, indicating that the scaling factor is working well. So here we go. Anomaly is going from -3 on the negative side to +4 on the positive side. So asymmetry exists. In the blue, we are looking at the traditional Nino 3.4, and the red line here is the relative Nino 3.4 or RONI index. So Nino 3.4 and RONI SST anomalies for 1982 to early 2026. Both indices are calculated from ERA5 SST dataset and are relative to a 1991 to 2020 climatology. So you can see the peak of the 82-83 El Nino is stronger in the RONI than the Nino 3.4, and there are differences here as well, and so is 86-87. This is 91, 92, larger difference than all of them, in fact. So you have to figure out why that is. So you can see they say the trend is smaller in the beginning. There is a however, there is a clear difference in the trend. For early years, relative index is higher, and for later years, it's lower. So you can see red line is higher here, but here it is lower. Okay, so the scaling is working in the sense that when warming is confounding Nino 3, which is stronger in this latter period, your RONI is reducing the amplitude of the traditional Nino 3.4 and increasing the negative amplitude of La Nina, so that you're not concluding that El Ninos are getting stronger and La Ninas are getting weaker. Understand? Some differences are expected even if there is no anomaly in the Pacific. Anomalous SSTs elsewhere, such as the Atlantic or Indian Oceans, can change the value of the tropical mean SST and hence the value of the relative Nino index. This can be considered a source of noise in the relative Nino index, as it is unrelated to El Nino variability. And every time you make a change, you have to deal with some consequence. The most recent El Nino in 2023 is about 0.5 degrees C weaker in the relative index, while the La Nina conditions of 2024 and 25 are stronger, as we saw here. Okay. Remember, these differences may seem small, but the amount of energy associated with them, when you consider the volume of water, then it's not trivial at all. Okay, so it's mostly the energy that makes a difference in the global perturbations, teleconnections, etc. Where was I? This can be considered a source of noise. As we said, the most recent El Nino in 2023 is about 0.5 degrees C weaker in the relative index, while the La Nina conditions of 24-25 are stronger. These changes reflect the intended effect of the relative index, which provides a more appropriate description of El Nino and La Nina in the context of a warming tropical background. Okay, it's not just tropical Pacific, so you have to be clear that when you say trop, Nino 4 is in the central tropical, deep tropical Pacific, whereas trop anomaly is 20 south, 20 north of the whole tropics. Okay, and make sure that you understand that. That's why we are saying even when tropical Pacific is not warming, Atlantic and Indian Ocean may have independent signals which are going to creep into your S times Nino minus trop, right? So keep that in mind. Where was I? Provide some more appropriate. From June 1, 2026, the relative Nino indices have been added to ECMWF's operational forecast plots from CS5, that's their forecast system. Relative versions of all four Nino indices, Nino 3.4, Nino 1. Nino 3.4, Nino 1 plus 2, Nino 3, and Nino 4 have been calculated with the same methodology to calculate an appropriate set of scaling factors for each of them. Forecasts of the relative index are typically 0.5 degrees C cooler than those of the traditional index. However, it's not simple offset, as each ensemble member has a different tropical mean SST, meaning each ensemble member has a different tropical mean SST, meaning I rewrote that, forget about it. Meaning each ensemble member is shifted by a different amount. So when you do predictions, you are doing ensemble predictions to capture the potential variations in real world. Mother Nature gives one realization, as we said, but the models try to perturb the initial conditions and capture potential evolutions Mother Nature could have given, could give, and each of those ensemble members have different warming patterns in the tropics. What are the limitations of a relative Nino index then? A relative Nino index has some definite advantages, but also it's not a panacea, never is in this tough business. Firstly, El Nino variability cannot be described by a single number, but it's convenient for public communications. Every El Nino event is different in terms of the detailed pattern of SST anomalies that emerges, as we have discussed already. In addition, the atmospheric response depends on the distribution of SST elsewhere in the tropics, as well as other sources of predictability in the climate system. When considering the likely impacts of an El Nino, this wider multidimensional context must be accounted for. So teleconnections are most important, because if El Nino happened in the middle of the ocean and nothing happened on land, we would probably not care. But because it makes such huge perturbations, droughts, floods, wildfires, health, etc., we worry about them. Secondly, the relative Nino index is sensitive to the conditions outside the equatorial Pacific. Most definitely, changes in the tropical Atlantic and Indian Oceans will alter the relative Nino index, even if they are completely unrelated to El Nino. We keep saying IOD is going to help the monsoon during an El Nino, for example, but IOD has its own pattern of warming and cooling in the tropics, and even though there is a separate debate about whether IOD is independent of El Nino, in this method, that tropical warming pattern is going to get into the relative Nino, right? Secondly, the relative Nino index is sensitive to conditions outside the equatorial Pacific, as we already said. This can be thought of as adding a certain amount of noise to an index designed to measure El Nino variability. Okay, finally, while the relative index largely removes the global warming signal from El Nino indices, this does not mean that global warming has been removed from the climate system. Absolute temperatures in the tropics have increased substantially over the recent decades, and absolute value of SST is a key determinant of evaporation, air temperature, the transport of moisture, and the release of latent heat. All of these are increased as the tropics warm, and both the response of the atmosphere to a given spatial pattern of SST anomalies and the subsequent impacts will differ as a consequence. We come back to our inability to use one number to describe our El Nino and its expected impacts. There is no simple and accurate method to compare present-day El Nino events with those of decades ago. This is a key message. There is no simple and accurate method to compare present-day El Nino events with those of decades ago. The entire system has changed in which El Nino is occurring. So it's not always a question of what global warming is doing to El Nino, but to remember that every weather and natural variability like El Nino is happening in a warmer world. So we are having an impact implicitly in all of them. Which observational estimate of SST do we use then? Astute observers will notice that observed values of Nino indices can differ depending on the source. This is true for both traditional and relative indices and stems from differences in the underlying SST data. So there are raw data, then graded data products are produced, sometimes by using reanalysis approach. There are optimal interpolations, all kinds of methods are used, and there are multiple products available, and they are not all exactly matching each other, even in the Nino 3 index, which is a large box averaged. So this is true for both traditional and relative indices in terms of the differences, and this stems from differences in underlying SST data. Sea surface temperature is not perfectly known, particularly for decades in the past with no or limited satellite data. We extrapolate back in time using some pattern assumptions. That's always problematic as well in terms of damping out the trends, etc. Different SST products use different calibration methods and different ways of dealing with the limitations of the past data in terms of gaps in space and time. We use the ERA 5 SST as the observational reference for CEAS-5. This is based on a relatively high resolution SST product, such as the Met Office's Hadley Center Sea Ice and Sea Surface Temperature Dataset or HADA-SST, and the operational Sea Surface Temperature and Ice Analysis or STIA system, which capture the full amplitude of variability in the Nino 3.4 area averaged SST, albeit at the expense of including a little noise in the earlier years. Okay, so CEAS-5 is the ECMWF system, just remember that. For the forthcoming CEAS-6 system upgrade, we will switch to using SST used as input to ERA 6. So that will have some two different analysis and reanalysis. So basically for near real-time use, you use the available data to do calibration, validation, and produce a product that is not research product. So you go and reprocess in a slower time period, and consistently long time scale SST is produced. So that's why you have analysis and another product, research product. Okay. These have similar characteristics, but is considered to be a little more accurate. Other Nino indices, notably the Oceanic Nino Index used by CPC NOAA, are based on smoother, lower resolution SST data sets designed to allow consistent analysis back as far as the 19th century. So they are more focusing on the longer term data set, and they produce reanalysis, atmospheric reanalysis based on those because you need SST forcing for atmospheric reanalysis. Then those reanalysis products can be used to force an ocean model to produce ocean SST, ocean reanalysis product, as well as as seen in SODA, which has a long-term reanalysis product as well. So this data has lower peaks for some of the major El Nino events of recent decades. This should be borne in mind if comparing ECMWF values to analysis produced elsewhere or forecasts which have been tuned to such analyses. So evolving and so monitoring, then the introduction of relative Nino indices provides a valuable perspective on ENSO variability, helping to replace El Nino and La Nina events in the context of a warming climate. By focusing on spatial differences across the tropics, these indices reduce sensitivity to long-term temperature trends while complementing existing measures. Developed as part of a broad international effort and recommended by the WMO, the new index RONI is expected to be readily adopted. Its arrival is timely, with current indicators pointing to a potentially significant El Nino event, possibly among the strongest seen in the past 50 years, underlining the importance of improved tools to monitor one of the climate system's most influential drivers. Okay, so just keep these things in mind, because this is science evolving in have a hiccup, somebody is remembering me. So these are evolving in real time, and we are tracking them because this big monster El Nino will be slightly reduced in RONI compared to Nino 3.4 to account for the background warming of the tropics. Okay, that's 30 minutes, but unfortunately we have to just live with it.